3, here we go. I'm going to start with the thing that I definitely forgot to come back to in the last video. I promised to define amplitude. First I'm going to define midline. Midline is the horizontal line through the middle. Pretty straightforward. The amplitude is the distance between, I should say the vertical distance, between the midline and the peak. So, amplitude is probably a word that you're familiar with from other things. If you do music, you're probably familiar with amplifiers. They make things bigger. That's what the amplitude does. It makes the thing bigger. Midline is pretty straightforward. There are two other transformations that we need to talk about today, and both of them are more strange than these two. These are the easy mode transformations. The other two are going to make things weird and interesting. So let's get right into those. Oh, let me also say, amplitude is the trig wave version of a vertical stretch. This is what we call this kind of transformation happening to any other function. We would call it a vertical stretch, but for a trig wave we call it the amplitude. Midline is a vertical shift. If it were happening to any other function, we would call it a vertical shift, but when it happens to a trig wave, we call it the midline of the trig function. Turns out all of the transformations have goofy names when we apply them to trig functions, most of them for good reason. So, let's talk about the next one. A standard sine function repeats every 2 pi units. 2 pi is called the period of the function. Also, the amplitude is 1, and the midline is y equals 0. These are the sort of standard default settings for a sine wave. The period is what we're going to mess with next. So we're going to talk about what happens if you try to squish more sine waves into the same amount of horizontal distance. So the period is sort of similar-ish to what we would call on other functions a horizontal stretch or squish. I hope that you have your notes for horizontal stretches and squishes available, because I'm going to assume that you all know how horizontal stretches and squishes work. So the first thing I want to do is I want to make a sine function that squeezes 3 full periods into this 2 pi. So I want to squish this 3x squished. 3 full periods in this same distance. So there are 3x, I'll say thinner, So horizontal transformations are the ones that, if we remember, work backwards than how you'd expect. Vertical transformations work exactly how you would expect. If you want something to be taller, you multiply it by a positive number. You multiply something by 4 to make it 4 times taller. If you want something to move up, you add. If you want something to move down, you subtract. This is intuitive. For horizontal transformations, they all work in a weird sort of counterintuitive way. If you want something to move to the right, a positive direction, you have to subtract on the inside of the function. If you want something to be wider, you have to divide. If you want something to be thinner, you have to multiply. The horizontal transformations are always backwards from what you'd expect. So if I want something to be thinner, maybe I should say, instead of 3 times thinner, perhaps I should say 1/3 as wide. It's tempting to want to create a sine function where you divide the x by 3, thinking that division is how you make things smaller. But that is not going to work. The horizontal stretches are counterintuitive, so we're going to do the opposite. We're going to say y equals the sine of 3x. And this, by the time x is 2 pi, this argument that we're taking the sine of, that's going to be 6 pi at that point. The thing inside the sine wave will have done 3 full rotations by the time x is 2 pi, because the thing inside sine is going to be 6 pi. So this is what's going to squeeze 3 full periods into the same space. So if this is 2 pi, then it's going to go up, down, back, up, down, back, up, down, back. So this function is going to have a amplitude is still 1, the midline is still y equals 0, and the period this time is 1/3 of the whole distance. This right here, let's see if I can highlight this one. I really need another colored marker. This one thing is 1 period, and that happens at 2 pi over 3. Between 2 pi over 3 and 4 pi over 3, we get our second period. Between 4 pi over 3 and 2 pi, this is 6 pi over 3, we get our third period. So we say that the period is 2 pi over 3. Generally speaking, whenever you see anything that looks like this, y equals the sine of bx, all of these different things have sort of letters associated with them, which I will deal with when I'm finished talking about them all as a group. Generally, when you have things that look like y equals the sine of bx, the period is always going to be 2 pi divided by b. So if b is 3, that means you're making it 3 times thinner, or 1/3 is wide. Then your period is 2 pi divided by 3, 2 pi times 1/3. If you put a fraction in here, as far as horizontal transformations go, putting a fraction in there would make this thing wider. Let me find a place to do that. Let's go back up here. If I do something like y equals the sine of 1/2 x, b is now 1/2, and the period of this function will be 2 pi divided by 1/2, because that's this 2 pi divided by b equation. So how do you divide by 1/2? You multiply by the reciprocal, which is the same as multiplying by 2. So, whoops. You get 4 pi as your period for this function. So, there's 2 pi, here's 4 pi. A standard sine function is going to go up and down and back up in 2 pi. This is the default. Our function is going to go up and down and back up. It completes one period in 4 pi horizontal units. So again, this is functionally the same as horizontal stretching and squishing, but we're not calling it that, we're calling it the period. And this one's actually fairly different. Instead of, before when we talked about the horizontal stretches and squishes, we talked about them in terms of like how many times thinner or times wider, you know, twice as wide or 3 times as wide, or, you know, half as wide, a third as wide. We always use these fractional comparisons, or multiplicative comparisons, I guess. For trig functions, we're not really going to talk about half as wide or twice as wide. We're going to talk about the period, which is the horizontal distance to complete one cycle. The horizontal distance before it starts repeating, I guess. So, this will give us our horizontal distance before it starts repeating. That's the period. And again, you can combine these period issues with other kinds of transformations, and you can get some pretty cool looking sine waves. I'll do one of those right now. And in fact, I think it's time I start experimenting with cosine as well. So let's just make up some numbers. Let's say y equals, I haven't put a fraction up front yet. Let's do 1/2 cosine of, I'll say, 2x plus 1. So, when you are graphing trig waves, I think the number one most important thing you can do is write down all of the different transformations. So in here, my amplitude is 1/2. My midline is y equals 1, and my period is going to be 2 pi divided by whatever this number is. So that'll just give me a period of pi. Once you have all of these things down, and there's a fourth one that we're going to talk about later that's going to make things really exciting, which is why we haven't saving that one for last. But once you have all of these things written down, you can start preparing what this graph is going to look like. So the midline is going to be 1. So here we go. This is that's positive 1. This is where you start, by drawing the midline. From here, you're going to think about how far above the midline does it go and how far below the midline does it go. And that's what the amplitude will tell you. So this thing is going to go half a unit up and half a unit down. So 1 and 1/2 is going to be its peak value. 1/2 is going to be its minimum value. It's going to be oscillating between these two things the whole time. If this ever touches your axis, you're doing something wrong. Next, we can look at the period. This thing is going to start at 0. It's going to end this many units later. So this is my full period. And then we need to think about what kind of function it is. In the other video, I mentioned that sine waves start in the middle and go up. Cosine waves start at the top and go down. So when this thing starts here at 0, it's going to be at its peak value. And it's always going to end at the same value it starts at. That's what it means to be periodic. And it's going to, in the middle, it's going to hit the bottom there. So, looks like this. Here's the thing that is really going to annoy me enormously if you do something like this on a test or a quiz. Lots of people tend to draw single periods of the cosine as if it was a parabola. They get this arc in the middle, and then on the left and right of this start and end point, they have it keep going up. Don't do that. This is a periodic function. This is its peak. It is turning around there and going down on the other side. Same here. Don't make it go up. That will make me sad. So this is how we can graph these functions. We still need to talk about one more kind of transformation that's going to make this thing even extra double exciting. So I'm going to dive straight into that right now. This is already kind of a long video, but you know what? No, I'm going to do another example with just these 3 transformations we have. Then I'm going to stop this and do a 4th video for the 4th transformation. Let's do a sine wave this time. Let's say that y equals, we'll do a big amplitude. 5 sines of 1/3 x plus 2. No, we'll do minus 2. Gotta get some fun negatives in there. Okay. So, we'll start with the amplitude is 5. The midline is -2. The period is 2 pi divided by 1/3, which is the same as 2 pi times 3, which is 6 pi. It's going to take this thing 6 pi units to do one complete cycle. So I'm going to start preparing my graph. Start with the midline. Should always start with the midline. Y equals -2 is our midline. And then you think about how high above the midline is it going to go and how far below the midline is it going to go. The amplitude will tell us that. At its peak, it's going to be 5 units above the midline. So from -2, that'll take us all the way up to 3. At its, I don't know the good word for this, minimum? Trough? Trough is the word I hear used a lot, but it doesn't sound good to say. At its minimum, this is going to be 5 units below the midline. So from -2, we'll drop down to -7. So 3, 4, 5, 6, 7. The period is going to tell us how far we have to go to complete one full cycle. So this thing's going to start at 0, and it's going to end at 6 pi. 3 pi will be right in the middle. And then we look at what kind of function we have. This is a sine wave. Sine waves start in the middle and go up. They hit the middle in the middle, then they go down, and they always end where they start. So we have a sine wave that looks like this. This is the point 3 pi over 2. It's right between 0 and 3 pi. Comma 3. this is the point, what's in between these 4.5 pi, so 9 pi over 2, negative 7. This should be a multiplication sign. So, this is how we can graph some sine cosine waves based on these three transformations. Part 4 is incoming, and that'll cover the fourth transformation, and then I'll make sort of like a bullet pointed list for how this process goes step by step.